Okay, so first of all, I would like to thank Radu for the invitation to come to for me to come to Vienna. Okay, so I'm going to talk about KR exponents for a class of so-called Hadamard-difference-parameterized models. I guess Guoyin already mentioned Hadamard-parameterization yesterday, but still we have another term, Hadamard-difference-parameterization. Of course, we can add more products, whatever. So first of all, I would like to introduce some of my co-authors here. So Yuncheng Liu, he's currently my postdoc. He's from Sichuan, he's from Southwest Minzu University in China. And Wenqing Ouyang, he is a visiting student from CUHK Shenzhen. And I can modestly and honestly say that he's actually the main guy doing everything. Okay. I'm essentially just paying the salary. and also Hao Wang from Shanghai Tech University. So what's Hadamard-difference-parameterization, Hadamard-parameterization, these kind of alien things? Well, they are really just a special case of a more general concept known as over-parameterization. And when it comes to over-parameterization, I think the most famous model would be training deep neural network. And this is not the focus of today's talk. Okay, I just put this thing here to keep myself awake while standing here, and also to sort of give an example of over-parameterization in practice. Okay, so well, there will be m data points. Okay, I think I probably steal some of the formula from some other papers. So usually it's in form of a picture, but so here there are m different data points, and well, there will be some so-called activation functions that you choose, like sigmoid or ReLU. Now, the thing is that there's a big L over there, which is this the pointer here? Yeah, the big L, which is sort of the depth of the neural network, which is typically very huge. And we try to solve this sort of best fit problem by finding suitable affine maps. So L of them, so there can be a lot of affine maps, and each affine map would have dimension PL by PL minus 1 whatsoever, which can also be huge. So there will be a lot of parameters, way more than essentially necessary to make sense, try to make sense out of these m data points. Okay, a lot of parameters. So it might sound counterintuitive why we want to consider such a high dimension optimization problem, but there have been some empirical or even theoretical studies on the benefits or some desirable properties of over-parameterized models. For example, the solution you obtain may enjoy better generalization error, and there could be implicit regularization going on in the solution. Okay. Now let's come back to Earth. Okay, so this is the model we are going to talk about today. Okay, now the world suddenly becomes very simple. So I would like to try to minimize this little f, okay, which is just the sum of a twice continuously differentiable function, okay, with L1 regularizer. And the capital G is sort of the over-parameterized model here of today. I will change this a little bit later. Now, basically, you can see that I'm changing the x by the Hadamard product of u and v. So I'm using 2 copies of vectors to represent 1 vector. So yeah, that's sort of over-parameterizing it. And instead of L1, I'm doing a sum of squares here. Okay. So you can see immediately that the capital G would be greater than or equal to the little f when you plug in the Hadamard product. And they have the same infimum value, just a consequence of AMGM inequality. So instead of trying to minimize the little f, I can also go ahead to try to minimize capital G. They have the same infimum value. Now, this little f commonly arises in compressed sensing variable selections, and the h is the loss functions. It can be logistic loss functions, least squares loss functions. These are convex stuff. We can also use Cauchy loss function, which would be non-convex. Now, this capital G is what is called the Hadamard parameterization. And the interesting thing is this G is smooth. Okay? And the smoothness has been exploited for algorithmic design. And the smoothness actually a little bit different from Nesterov type smoothing. As you can see here, there's no smoothing parameters that you need to drive to 0. So this is more like an exact smooth reformulation of the original problem. And now here is the Hadamard-difference-parameterization. So this is really just a reformulation of the problem so that we can get a form that is easier for our analysis in the paper. So just to introduce the notation to be consistent with what we work with in our paper. So take the UV and do this invertible linear transformation to get two vectors A and B. Okay. Now when you do the substitution, after some work, you will get this capital F, where this A square is entry-wise square of the vector. Okay. And this is not a typo, okay? So when you plug in, the 2 is actually gone. So this is not a typo. There's no 2 there. Now this capital F is called Hadamard-difference-parameterization. And because it is just related to capital G via an invertible linear map, so when we study properties such as first order stationarity, second order stationarity, and K exponent, which are actually invariant under invertible linear transformation, it doesn't really matter which one we study, capital G or capital F. And in our paper, it turns out that working with capital F is easier. So we'll stick with capital F. Now there are 2 questions that I would like to ask and answer. Well, we have the capital F. Capital F is C2, so you can go ahead to do Newton if you want. Okay. So you'll get some stationary points of capital F. So how do those things correspond to stationary points of little f? Now the second one is a little bit more technical. Well, we know that there have been already a lot of efficient algorithms for minimizing little f, proximal gradient, proximal Newton, and a lot of line search variant, trust region based variant kind of things. Now, let's say if we can get a stationary point of little f sort of efficiently, okay? What can we say when we try to work with capital F instead? Now, to be more precise, let's say when you try to apply proximal gradient to minimizing little f, you get sequence that's, well, linearly convergent or locally linearly convergent. Now, what happens when you try to apply an analog of proximal gradient to capital F? Well, that would be steepest descent. Okay, would you still get something converging locally linearly, something like that? Okay, some sort of convergence rate inheritance issue. Well, it's just in the analysis. It's cleaner. It's cleaner. Okay, so 2 questions: stationary point inheritance and also the convergence rate inheritance. So let's start with the first one. Okay, it turns out that we will need to look at second order stationary points. Okay. So when you look at second order stationary points of capital F, and well, form this guy S, okay, which is basically this thing over here. So A squared minus B squared. Now then this S would be a stationary point of little f. Okay? And also the decomposition must be very efficient in the sense that we will decompose 5 as 5 minus 0 instead of 6 minus 1. Okay, this is what this mean is talking about. This is entry-wise minimum. Okay, so one of the entries has to be 0. And when we restrict our attention to the support, the Hessian of the loss function would be positive semi-definite. And I need to point out that it is not enough to just look at stationary points of capital F, okay? Just first order stationary point, the corresponding S may not be stationary for little f. Okay. Now when H is convex, and we know that little f is convex, so stationary points would be globally optimal. Now capital F would not be convex in general, even when H is convex, But still, we have the equivalence between bullet points 3 and 4. Well, actually, all 4 points are equivalent. So basically, any second-order stationary point would be global minimizers. And the title of slide says strict saddle property. This thing actually sort of corresponds to bullet point number 1. So if I read the equivalence between bullet point number 1 and number 4, sort of in the opposite way, it basically means that if you are at a stationary point that is not second-order stationary, then the minimum eigenvalue of the Hessian would be uniformly negative. So there will be a uniform negative curvature direction. Okay, so this delta is actually independent of AB. It only depends on the solution set structure of little f. So this result was established earlier already in Karen Spoon's joint work with her co-authors in the case when H is convex and quadratic. So we are just doing this for convex and C2. So that's the stationary point issue. Okay, and then we get to the convergence rate inheritance issue. Now, when it comes to convergence rate, of course, I will be talking about KL property and exponents. And of course, we are about the time for the coffee break. So I would not go through this definition. But basically, I just want to point out that this alpha would be the thing that we will be looking at today, which we call the KL exponent. Okay, and well, to explicitly determine this alpha for a given function is typically not easy. So this bullet point number 2 example here is one of the few examples that we actually have explicit KL exponents. So I'm citing a work by Woyin, Boris, and Pham. Okay, so that's the maximum of m polynomials of degree at most d. So that's the explicit formula for the KL exponent. I think it's the same. So yes.
This is a particular case because you fix the exponent.
Yeah. Yeah, thank you.
No, it is, but it is a particular.
Okay, thank you. Okay, and the exponents, of course, I think we have seen this several times already in this workshop, in Boris' talk and also in Guoyin's talk. Okay, that this exponent has to do with qualitative convergence behavior of the sequence generator. Okay, so now our question is about convergence rate inheritance. And of course, it's not very easy because convergence rate depends on how close you start to the solution and things like that. So I would like to talk about something a little bit more intrinsic, which is, well, the KL exponent. So now the second question is changed to this. So would there be any transfer principle for the KL exponent? Okay. So the KL exponent of little f in the form that we are looking at is actually known for many functions, many examples of H, like the least squares loss function, logistic loss function. Yeah, always these two examples. And that's actually 1/2. So can we deduce the KL exponent of the corresponding Hadamard-difference-parameterized model? H is C2. Just C2, just C2. Yeah.
You could use the Clark differential.
Yeah.
Okay, but use
yes.
Why?
So that he does not ask why. Is there a better? I think the original is Clark, right? But then later on in 2010 in the MOR paper, they used limiting subdifferential. Okay. Anyways, okay. Yeah, it turns out that we can only say things about second-order stationary points of capital F, okay, which is not too surprising because is only these points such that the corresponding S star would correspond to a stationary point of little f. And typically, we would impose KL assumptions on stationary points of little f, okay? Because that's the only points that we make sense to impose particular assumptions on KL property. So assume that the KL exponent is alpha. Then, if we have the strict complementarity condition, okay, the thing I highlight in magenta, then capital F would satisfy KL property at A star B star with exponent essentially alpha, but you take the maximum between alpha and 1/2. Okay. 1/2 is typically what you would expect. Now, what happens if strict complementarity fails? Then we add some other assumptions, right? There's no free lunch. So here we would need to impose convexity of H, and then in this case, the little f would be convex. So we also assume that the set of global minimizers is polyhedral. Okay, so convexity assumption and polyhedrality assumption. And the KL exponent of capital F would be given by this, 1 plus alpha divided by 2. Okay, so there's an interesting formula over here. Okay. So just a remark about polyhedrality assumption. So it's not too restrictive because if you take the loss function to be the composition of a strictly convex function with a linear map, then it will hold. Now then, of course, the next obvious question is why this exponent, right? Why not 3 plus alpha divided by 4 or some other interesting formula? Well, we have an example, okay, at least saying that under the conditions when H is convex and omega is polyhedral, this is the best you can do. Okay, alpha also has to be greater than or equal to 1/2. Okay, so one more condition. So this is the example. So you take H to be this one-dimensional function, which you can check immediately by taking second derivative that is convex. And this is the little f. So I'm just adding the absolute value X regularizer, mu is 1. And using some triangle inequalities should be pretty easy to see that the minimizer would be singleton set 0, so that's polyhedral. Okay, so convexity polyhedral. Now, little f is not differentiable only at the origin. So if you try to, I try to write down the definition of f into 2 pieces. So this is what it is, and that's the derivative, which I just forget about 0. Now, you can see that for the negative part, okay, for the negative part, the derivative in absolute value is always at least 2. So when we talk about KL property, we can forget about the negative branch. Just look at the positive branch. And so compare this one with this one, then the exponent is alpha, the origin. And how about the capital F then? Well, in the definition of this H, we have this minus x over here. So we plug a squared minus b squared into this x. So this is what's going on here. And then you get this expression. Now, if we restrict our attention to the path t0, and this is what the gradient looks like, what the function value looks like, and we will have this equality over here, and you see that this exponent pops up. Okay. So this shows that at least we will need this exponent, okay, for KL properties to hold, and from our theorem, we know that this exponent would work. Okay, so this is the tight exponent. Now, before moving on, well, which is actually one more slide only, let me also point out explicitly that our results actually do obtain KL exponents of some functions that whose exponent were previously unknown. So again, these 2 loss functions, okay, yeah, we can have more. And now if you use this, the least squares loss and the logistic loss function, then the odd mean would be polyhedral and KL exponent is 1/2. And so based on our work, depending on whether we have the strict complementarity condition or not, the exponent would be either 1/2 or 3/4. Okay, but this is just a second-order stationary point, right? And suppose I'm a diehard, I want to use first-order method. Okay. Well, then how can we make use of the KR exponents as second-order stationary points? Well, there are a lot of existing work saying that if you use even if you use first-order method, okay, as long as you do some random perturbation or maybe you use some random initialization, you're going to get to second-order stationary points. So we're essentially following that path, except that there is a tiny little trick, because in most of the existing work, if not all, typically they require the gradient of the function to be globally Lipschitz, so that they do constant step size. Maybe that's easier for analysis. Now, for our f, the gradient is not necessarily globally Lipschitz, so we need to do some backtracking, but that's pretty much all we did. We essentially just adapt to the existing analysis with a little bit of backtracking. Okay, so here's the condition. So we assume that H is subanalytic, and well, in the blanket, H is C2. Okay, so C2 and subanalytic, and lower bounded, so that this F would be actually level bounded. And we consider steepest descent with backtracking, line search. The line search is a major rule, okay, and then the initial step size of the next iteration is just the existing step size. And there are two things that we set random here. So the initial step size and also the initial point. And almost surely we get convergence to second-order stationary points, and so the convergence rate will be governed by the KR exponents we obtained. Okay, so everything I discussed can be found in this preprint available on arXiv, well, except for the last theorem 5, okay, which we will update hopefully in the next 2 weeks, okay, onto arXiv. So that's all. Thank you for your attention.